refraction and attenuation. Troposphere is the lowest part of Earth's atmosphere. In troposphere, temperature decreases with altitude, and this decreases with 5 to 6 degrees per kilometer. There are meteorological phenomena in this layer of atmosphere, like clouds, rain, turbulence. The upper limit of troposphere varies between 8 kilometers at the poles to 11 kilometers at the equator, and troposphere could be divided into 2 layers. Lower layer is turbulent layer. It is to 1.5 kilometers from Earth's surface, and then next layer is free atmosphere. In this free atmosphere there is no turbulence. Turbulence is one of the phenomena that is very important for wave propagation, for radio waves and for optical waves too. But here we speak about radio waves mainly. What is interesting in this lower layer of Earth's atmosphere, we have one parameter that is called refractive index. This n and it is square root of dielectric constant multiplied by magnetic constant, and because for the air magnetic constant, relative magnetic constant is 1, it is square root of dielectric constant. Dielectric constant is almost 1, but it can vary in maybe 4th, 5th sign after decimal point, and this variations are very important for radio wave propagations. Because this is something .003 around this value, this n. It is better to use this one. This is refractivity of the Earth atmosphere, and this is small n minus 1 multiplied by 10 in power of 6, or this n is around 300. It is it gives us more information than small n or refractive index, and this refractivity, as you could see from the relation in the right side of the screen, depends on P, that is atmospheric pressure, from absolute temperature, T, and also from water vapor partial pressure. And these three parameters vary with the height in the troposphere. We said that temperature decrease in normal condition decrease with 5 to 6 degrees per kilometers. Atmospheric pressure also decrease on barometric formula, you know this, and humidity, it depends on humidity of the air, and humidity also vary in different conditions. When you have, for example, lower clouds, it could be higher. When the weather is like these days, it is also high level of humidity, but in some sunny days the humidity is smaller. So these parameters lead to variations of refractivity, and this refractivity causes something very important for wave propagation. I will try to explain. There are two explanations of this. One is with geometrical optics, and other one is with wave theory. So we have troposphere divided by two very thin layers. Here in first layer we have refractivity N1, in second layer N2, N3, etc. So in a lower part of the atmosphere we have higher pressure, atmospheric pressure, and therefore the dielectric constant is a little bit higher in normal conditions, a little bit higher than on a higher level of the atmosphere. So if radio wave propagates in these layers, if this is the path in first layer, in every layer the refractivity is the same, and it changes very small from layer to layer. So this is the propagation direction. In second layer, if the electric constant was the same, this will be the direction, but because it changes, the direction will change a little bit. Then in next layer also will change a little bit, and like in ionosphere, here the electromagnetic wave start to bend to the Earth's surface, but not every time to the Earth's surface. And this is called tropospheric refraction. And this is caused by different pressure, temperature, and humidity at the different height in the troposphere. This is one explanation with geometrical option. Other one, if this is wavefront, this is propagation direction. Propagation direction is perpendicular to wavefront. Here, wavefront is higher in the Earth atmosphere, Earth troposphere than there. Phase velocity is equal to speed of light over the square root of the electric constant over n. But here and here the electric constant is different. Here the electric constant is bigger than here in normal conditions, because here the air density is higher than here. So this speed will be smaller than this one. Do you agree? Here the electric constant is bigger than here, and therefore here for lower part of wavefront, phase velocity is smaller than for upper part of the wavefront. So, because this part of the wave will propagate with small velocity, the Earth front will be like this in second moment and like this in this moment. Or in this case, propagation direction will be this one. Or we could see that radio waves propagates not in straight line, but in some curve that we could approximate with a part of circle with a radius that is given here. This is Greek letter rho. This radius is very big, around 35-50,000 kilometers. Radius of the Earth is 6.37, approximately 1,000 kilometers. So this is 4 to 8 times bigger, but in some time it is different. We will see this. And this is the radius of this curve, that is radio wave part in the troposphere. So a refraction, tropospheric refraction, is this phenomenon, change of wave path caused by temperature, pressure and humidity changes in the height of atmosphere. So, if we see this formula, this is clear. This every time always decrease with the head pressure. But sometimes temperature increase with the height. You know that sometimes there is temperature inversion, and in high altitude the temperature is higher than in low altitude. Sometimes the gradient of temperature is not 5-6 degrees per kilometer, but bigger, maybe 10, 12 degrees per kilometer, and that leads to variation of this path and variation of radius of this path. So almost the whole electromagnetic wave propagation theory is based on straight propagation of radio waves. But here we have not straight line propagation, but some other part of radio lines. How to solve this problem? That the whole theory we have to put it in the trash. This is decision of the problem, effective Earth radius. This is part of the wave in the troposphere. This is straight line, and this is a real Earth surface. We start to how to say помагайте углом как bend. Это наклоним по-скоро. Добре. To bend these two curves at the same time to the moment when this path is straight line. In this case, we will have different Earth radius, or we will assume that radio waves propagate on straight lines, but over Earth surface with different radius. So everything we have to change is a radius of the Earth. In every model that we obtained, we have to replace a real Earth radius with effective Earth radius. And in this way, we could solve this problem with different propagation paths. To make this substitution, this is the mathematical equation that could be fulfilled.
Are the this is due to the effects of the troposphere. Are those effects also stochastic?
Yes.
Their nature is, but they can be measured, I guess?
There is some statistic about this different type of you could see
the equation on the previous page was giving us two terms, one due to the pressure change, which is not stochastic, and the other one is due to the water vapor.
Yes.
Which it, by nature could be stochastic, right? Because you don't know how much water vapor there is. Is there any other terms that are in this?
Yes, it is absolutely stochastic, but it is in next part we will speak about. I will speak about different type of refraction, and then I will say you something about this. So for now, this is curvature of Earth surface 1 over radius. This is curvature of real trajectory, and this would be equal to difference between curvature of equivalent or effective Earth and minus curvature of effective path. But effective path has a radius infinity, and 1 over infinity is 0, and therefore here is not 1 over 1 over r minus 1 over path is 1 over equivalent, and because this is infinity, this one is z. So from this equation we could obtain the value of effective Earth radius. And I go to 8.1 for more. This is our this is gradient of refractive index. It depends of gradient of on gradient of on it's very refractive index after 5 hours speaking. So this is path radius, and depending on this gradient, sometimes refractive index is higher on high altitude. Normally it is small, but in some cases it is higher. In some cases this gradient is very big, in some cases is small. So we have different type of refraction. And here I explain some main type of refraction. Main types are here: subrefraction, zero refraction, normal refraction, and superrefraction. Subrefraction. In subrefraction, this gradient is positive. The case I mentioned when n increase with the height. In this case, path radius is negative, or this is the wave path. It bends to the space, not to the earth. And in this case, effective radius is smaller. Here, effective radius is smaller than real radius of the earth. Zero refraction, it is the case when path is straight line. no refraction. Then, normal refraction. This refraction occurs in normal conditions in the Earth troposphere. These normal conditions are temperature at the Earth's surface on sea level 15 degrees centigrade and 5.5 degrees Celsius and decrease of temperature per kilometer in the troposphere, and atmospheric pressure 1032 millibars on sea level, and it decreases with barometric formula and constant humidity, relative humidity in the troposphere. That is normal atmosphere. In this case, we have normal tropospheric refraction. This gradient is minus 0.04. Path radius is 25,000 kilometers, and effective Earth radius is 8,500 kilometers. This is real Earth radius, and this is path of the radio wave, and this is effective Earth and effective radio wave path. So the last one is not last one, but there are one that is called critical refraction, but in some cases it is called super refraction. It is a little bit difference between these two refractions. Critical refraction, in this case, the curve of path is parallel to Earth surface, or this is equivalent picture. Earth surface is plane, and radio wave propagates over plane surface. And the last one is super refraction. In this case, the radius of wave path is smaller than radius of Earth surface, and this is equivalent Earth, and this is equivalent path, the strand line. So if we draw distribution, here is normal refraction, and this is distribution. Here is negative. Here is super refraction. That is statistic. In most cases, the refraction is normal, but around maybe 1-2% of time we have negative and super refraction. For radio links, negative refraction is very bad conditions, because if we have some line and here we have some obstacle, and this is the path in normal conditions. If we have subrefraction, the path will be like this, and in this case we have free line of sight. In this case, when we have negative refraction, line of sight is not free because this is propagation path. So negative refraction is not good for radio links, but in some cases we have also super refraction. That is the other end of this figure. Super refraction is also has also negative role in radio wave propagation, because in this case we have problems with electromagnetic compatibility. What is the problem? Here, for example, we have some transmitter, and we want to listen the radio from this transmitter, and we are in the working area of this transmitter, and in distance of, for example, 100 kilometers, there is other transmitter that works at the same frequency. It is usual for radio communications to use the same frequency in different regions when the distance is enough. But if we have super refraction, the radio waves from this transmitter that is at 100 kilometers will propagate to this place, and here we will receive signal from transmitter that we want to listen, and from other one that is with different working area. And this is problem with electromagnetic compatibility. So super refraction lead to this. In optical region, optical waves, the mirages in the deserts are caused by super refraction. You see something that is far away from us, from you. The problem is super refraction. So that is the statistic of refraction. Is this was your question or?
Yeah. So basically in the first scenario we'll have not enough of propagation. If we are transmitting something from, let's say, 300 meters and we want to expect to receive it at 300 meters, it will not reach. And in the last scenario, if we have multiple towers per 300 meters, we'll receive information from this one, from the second, and from all the
Yes, and that is the problem. But everything in radio communication is depends on stochastic conditions, because Earth atmosphere is everything, weather, sun activity, and everything is stochastic.
So if you want to have a reliable link to send information constantly, you have to have a dynamic way of calculating all these parameters and making adjustments. Or is this not how it's solved?
We used also stochastic stochastic information. Now I will speak about rain attenuation. We have different rates, and you know that heavy rains occurs in very small time for a given period. If we have 1 year period, for example, very heavy rain we will have, for example, for 1 minute this year, and we use some rain rate level to calculate the link budget of the radio link. It is possible to rain heavy than this rain rate that we take into consideration for link budget. But this is part of the game. For example, for 10 seconds per year, our link will interrupt. But in other case, we will pay more and more. And it could rain heavy and heavy. We don't have we will be not absolutely sure that you will not rain more heavy that we take into consideration. For example, if we have, I will explain this after that one when we talk about rain attenuation. But this case is the same. When we calculate some links, we calculate it for normal refraction, because this is the most often happened case, and then we make calculation for this case and for this case to know what will happen in this case, in these two extreme cases. That is situation. So, tropospheric scatter. This is because of turbulence. Because of turbulence, we have some volumes in the air where the dielectric constant is a little bit different than in other air here around this volume. So this a little bit different dielectric constant causes scattering of radio wave in different directions. The angle of scattering is very small, but if during its propagation this radio wave meet some turbulence areas, it will change its direction, and in this case we could make radio links behind horizon. It is used, for example, in the army and also in some petrol platform in the oceans. In very big distances, around 500 and more kilometers, and at frequencies from 500 megahertz to 1 gigahertz, where the normal propagation distance is around 40-60 kilometers. We could make links with distance around 500 kilometers, but the powers is maybe about 20 to 50 kilowatts, and antenna diameter is around 20 meters. For other links that are 40 to 60 kilometers, the power is around 1 watt, and antenna diameters is around 2 meters. 2 meters. That's the difference. And this is very interesting phenomenon. This is called tropospheric ducting. Here we have some layer with layer with warm air, and when radio wave propagates in this area, it reflects from upper part, then from lower part, and propagates in this layer, and also propagates on very high, on very long distances. For example, sometimes in the summer, in central part of Bulgaria, you could receive radio station from Turkey, or mainly from Turkey, because in Greece there is a problem with the mountain Rhodope, but from Turkey the mountains are lower, and therefore there is no problem with that. But this happens sometimes in summer months, when the weather is very warm. This happens, and also we have such a tropospheric ducting over the sea. That is very interesting also, also in summertime, because of high temperatures in the summer. The humidity in the air over the sea is very high. It is almost 100% relative humidity. And in upper part, the humidity the gradient of humidity is very high, and it decreases very fast with the altitude. Therefore, if this is the sea level, the sea surface, we have one layer here with very high humidity, or here the electric constant is not so much, but if here is epsilon r 0, here is epsilon r, this is bigger enough than this one. So we transmit signal, it reflects from this, then from sea surface, then again, and we have waveguide from the sea and this layer with high humidity over sea level. And this causes propagation on very big distances. For example, maybe 5 or 6 years ago, one of Bulgarian mobile operators had a problem with some interference on frequency band, I think around 870 megahertz. That is the lower part of GSM band, then was GSM band. And we worked at this problem, and the problem was in the Ukraine. Some operator in Odessa worked with GSM technology, but on standard that is used in United States. And for this standard, the uplink was around 800 megahertz, and downlink was around 870 megahertz, whereas uplink of our GSM standard. And this signal from base station in Odessa propagates over sea to the north part of Black Sea coast in Bulgaria. And if you are here, it is almost impossible to use your mobile phone in these frequencies, because you have signal, but it's impossible to make a connection with your mobile phone. And that was the problem. Also, if you are at the sea, you could listen to Turkish radio stations, maybe in the north part of Bulgaria, because of this phenomenon also, and on maybe Romanian on some other radio station if you are down in south part of Black Sea coast. So on the sea, the propagation conditions are very different from the Earth surface, and they are very good according to other case when we have Earth surface, because sea doesn't have relief also, there is no obstacles, and radio waves propagates on maybe more than 10 times bigger distances than at other part of the Earth surface.
So how was the problem solved? Was it with antennas which were again stronger to the...
No. Maybe in the past there is the same problem. The first I see that was in 1989 when I was in the army in Shabla, and we received Turkish TV in the north part of Bulgarian coast. That is maybe in that time the direction of some antennas was were to Bulgaria, but now I think it is not the problem. The problem is this, that propagation conditions are very good for over sea, but not over Earth surface. Yeah, after. Hydrometeors and atmospheric gases attenuation. We have two phenomena that cause attenuation of radio waves in hydrometeors and atmospheric molecules. Absorption, part of radio wave power, is transformed to the heat in more cases, and other is diffusion and scattering or scattering. Radio waves scatter in different direction when it meet some molecule or some water particle. Hydrometeors are rain, snow, hail, fog, and clouds, or water object with different size. And these two mechanisms cause attenuation of radio waves. Hydrometeors. Clouds and fog. Clouds and fog are almost the same. Particles in the clouds and fog are with the same size. It is smaller than 60 micrometers. If they are with bigger size, they will fall to the Earth's surface like rain or snow. And because of this small size of particles, clouds and fog affect radio wave propagation at frequencies higher than 100 GHz, and this effect is very, very small. They affect more optical waves. You know that if there are fog, you see
No astronomy.
Yes, no astronomy, no optical astronomy,
No
but
optical.
radio astronomy is possible. That is the situation with clouds and fog. They affect mainly optical waves, but not so much radio waves. Rain. This is the more often phenomena connected with hydrometeors. It affects the radio wave with frequencies higher than 3 GHz. For lower frequencies, practically there is no attenuation of radio waves in the hydrometeors. To 10 GHz, it is not significant, it is small, but when we calculate some radio link, we have to take into consideration rain attenuation. But for frequencies higher than 10 GHz, it is very high for heavy rains. For light rains, it is not so high, but for heavy rains, it is problem. Around 30 years ago, when we received signals from some sport event like Wimbledon, for example, in some TVs, they used satellite for this, and the signal was analog, not digital, as it is now. And then in the summer, where is the Wimbledon tennis match? No match, but tournament. When there were the heavy rain, the signal disappeared because then these satellites didn't transmit so strong signal for our part of Europe. They are focused on the west part of Europe, and therefore the local TVs used big antennas, and signal was with critical level, and if it started to rain, everything disappeared. So this is the problem. Satellite TV uses the frequencies around 12 gigahertz, a little bit higher than 10 gigahertz, and in this case the attenuation is high, and this is the main this cause decreasing the flick distance. For example, at 6 gigahertz, the link distance could be almost to the line of sight, to the horizon. But at 15 gigahertz, it is maybe 60% of the distance to the horizon because of this. If in first case it is 60 kilometers, in second case it could be max 40 kilometers. Because if we have heavy rain, the attenuation will be very high, and the link will interrupt.
Okay, but why the satellite dishes for the satellite TV, the new one DTH antennas, are 60 and 80 centimeters?
Yes, because
and before
now
they were 2 meters.
because now we have satellites that transmitted to the
Higher power.
Bulgaria,
To Bulgaria.
to our part of Europe. In the past, we received signal from the satellites that are focused to the
Central Europe.
central or west part of Europe. But now there is satellites, there's Greek satellites, Turkish satellite, and Bulgarian satellite, Bulgaria sat, not Bulsat, Bulgaria sat that are focused on our part of Europe, and therefore we could use 60 centimeters, and when the rain is heavy, there is a problem.
Yeah, because there will be above 10 gigahertz.
Yes. If you have satellite link, free space losses are around 200 decibels. I don't know if you know what is decibel, but 200 decibels are 10 orders of attenuation. If you transmit power signal with power 1 watt, you will receive signal with power 10
To the
minus 10 watts. And attenuation due to rain is max maybe 10 decibels, and this is 1 order. Very small in comparison with the free space loss, because distance is 36,000 kilometers to the satellite from equator. But the link budget is calculated very close to these levels, and if the rain is very heavy, the link could interrupt. Also, if on the place where is uplink also rains, and when you at the place where you receive the signal also rain,
twice.
in this case there is a problem, but these operators prefer to use smaller dishes because it is cheaper. If they use 90 centimeter dishes, I think they will not have the problem, but that is the situation. So, snow and hail. The situation for snow and hail is almost the same like in rain, but the difference is that snow is not so intensive like rain. Rain rate is measured in units millimeter per hour. You maybe know this. This is equal to liter per square meter per hour.
Yes.
So, if you have rain and snow, very heavy snow, it seems like very heavy snow, but the water, the quantity of water is not so big as in the rain. It is like medium heavy rain. That is difference. In hail, it is the opposite. In more cases where you have the hail, it is with very heavy rain, or before hail or after hail there are very heavy rain. But this is not so often. It happens not so often like rain, and snow is also not so often as rain. Rain is main precipitation, so we use rain for calculation of radio links. Here is given attenuation per watt per kilometer for different rain rates, and here the max is around 100 gigahertz to 200 gigahertz. In 100 gigahertz, the wave length is 3 millimeters. In 200 is 1.5 millimeters. The most of raindrops in the rain are with the same size, 1.5 for 3 millimeters. And therefore the max of attenuation is for these frequencies. And one more thing about depolarization. What is the shape of raindrop? That is in kids' books. This. Because of air
Friction.
Yes. This is the shape of raindrop. And therefore, attenuation for horizontal polarization is bigger than attenuation for vertical polarization. And if this is direction of polarization, for example, this will be horizontal component, a little bit higher will be vertical one, and after the rain, maybe this will be the polarization of the wave. Horizontal size is higher than vertical size of raindrop. Max size of raindrops is around 7 millimeters radius. If they are bigger radius, they they separate to 2 drops, and that is max size of the raindrops. So maybe 5 minutes rest.